Everybody had good Thanksgiving? Food tasted better. The air was brighter, fresher. Yes, the air was brighter. The sun was brighter. More clean. Yes, yeah. Everything was better. You have a good weekend, right? Okay, so this week is a week of just review. I don't have intent or plan to introduce anything new. And so what I plan to do over the next Monday, Wednesday, Friday is go over one of the final exams. And so this was the exam from last semester. And there were a total of 12 problems. And I'm just going to cover 4 of them today. We'll do 4 more on Wednesday and then 4 more on Friday. Okay. And of course, there's always the question, well, is the final going to look like is this one? And the answer is they pay me a very good salary to be creative and keep the material fresh. So probably if you look at this exam and look at some, you'll see some similarities because the material, of course, hasn't changed in several decades. But there are also some wrinkles. And so it's not that they're intended to be tricky, but what I'm going to try to do is to cover just primarily the principles that are covered so that you know what we're looking for. My advice to students is try not to look for patterns in problems. If you're trying to reproduce a pattern and a mechanism for trying to solve a problem, then when the problem changes a little bit, then it'll throw you off. But try to ask yourself, do I understand the underlying principles of each problem? And that's what I'll try to cover today. I also have the exam 4 graded, and so I'll return that today. And when I looked at the calendar, my understanding is the design project is due Friday. Yes? Okay, so just bring it in to class Friday. I'll try to work over the weekend and grade them. I hope I'll have them graded by next week, or early enough for you to decide whether or not you plan to take the final exam. Well, actually, everybody takes the final exam, but you may choose to bomb the final exam if you want to. Okay. Yeah, the university says I'm supposed to give a final exam, and so you all know. All right? Yes. Yeah. So, any questions about what we're going to do? Okay. So we're just going to cover 4 problems today. It'll probably go pretty quickly, and then I'll go over. I'll return the final exam to you. Exam 4. Exam 4 has been posted. Also, the solution has been posted. So this was from spring. All right, so let's go ahead and move forward. I think the policy is we'll allow, again, 2 sheets of notes for the final. Okay, so one of the first things that we have to understand is in system analysis is what is the concept of a transfer function? What does this mean? What does this word mean? What does the word transfer function mean? And it's describing the relationships between 2 signals. And so we have to understand what is the definition. Okay, so you need to understand what is the definition of a transfer function. And as electrical engineers, I feel like one of the things that distinguishes from the rest of the world is that we at least understand how to analyze circuits. And so almost always this is a circuits problem. But if you look at some of the old ones, exams, there may have been a very simple mechanical circuit. So you might want to put it in here. Could be a mechanical problem, a mechanics. Could be a mechanics problem. There was a homework problem, a couple homework problems where there were simple mechanics problems. The principles are still the same. Okay, and so you'll notice that here initial conditions are given. Okay, and we use notation where this is time. This is time. Okay, so these are time notations. Time t equal to 0. And so the lowercase refers to basically time domain. But we have to understand that what we're looking for is a relationship describing the relationship between output and input. And so what we seek
here basically is a relationship between the output, and we're going to write it as capital V of C in the S domain. Okay, now in communications, we probably would use the Fourier analysis, the omega instead of S. And Laplace uses a more general term, S. S is equal to not just omega, it's equal to omega plus a real part. In discrete time, this would be a Z character, but these are no longer in time. So this is a transform variable. Okay, so that's one of the concepts is that we need to understand is that this is a transform variable. It's not a time variable. Oh, and a lot of times we call this the frequency domain. We call it a frequency domain variable because in some transforms it has the meaning of frequency, but S is actually just a transform variable. What we seek, however, is a ratio between the output variable divided by the input variable. So we need to understand that what we're looking for is an answer to this. Okay? And we need to understand the definition. The definition says it's a ratio. It's a ratio in the transform domain. Secondly, the ratio is written that it's output over input, kind of like a gain. Okay, what is the relationship between output over input? And so I'm looking to see that we don't get this inverted, upside down, and that we're using the right notation. Okay. This particular problem has two inputs and several variables, all marked, IL, VC, and so forth. And what we're looking for is we need to understand that we're looking for a relationship between this output variable, which is this variable here, and this input variable, I1, which is this variable here. And so we need to understand what to do with other variables, and they should not appear in the transfer function expression. In this particular case, we have two inputs, and so one of the principles that we should apply here is we should apply the principle of superposition, which means that we can treat inputs one at a time. And so since we're only interested in the relationship between this input and that output, we can ignore the effects of this input. And so we need to know the proper way to ignore a input that we don't care about. And so in this particular case, we need to treat it as I2 is equal to 0. So we apply superposition here, and I2 is equal to 0, which we recall from circuit analysis is that it is an open circuit. Open circuit means it's basically taken out of the picture, and so immediately the problem becomes a little bit more simple. And this is the principle of superposition, is that we can make our life a little bit easier by applying superposition. In this particular case, we're looking for a voltage here, and so we would need to use some sort of circuit analysis tool that tells us what voltages are, solves for voltages. I know when we take this out, we may be tempted to say, well, look, I could find a loop current here and a loop current here, but if we find loop currents, we still have to do additional work to find voltages. So it would make sense, it would make our life easier to try using nodal analysis. And I'm going to just call this point A. Okay, at point A. Let's try a nodal equation. And so we would have to understand the correct science to write for this equation. If we take this out, the nodal equation here says that I2 is coming in, I2 of t, and then we have the currents flowing out. And so the current flowing out here is IL. And this is in time. And then a current flowing through here. And the current flowing through here is the capacitor current. I didn't label it, but we know it's equal to C dVc dt. Okay. And this current IL, we need to know the science for it. The science for it tells us that the relationship between current, and the voltage across the capacitor is 1 over L integral of the voltage across the inductor. But the voltage across the inductor is Vc, so we have Vc of t dt. Okay. So now we have basically, I'm sorry, this is I1, not I2. This is I1. We have an equation where we have just voltage and current, just voltage and current, but this is in the time domain. And then the next concept is we need to understand Laplace transform principle. Okay. We need to do the Laplace transform. And so the Laplace transform tells us that I1 of t becomes I1 of s, and Vc of t becomes capital Vc of s. And then what about these derivatives and integrals? And so we're looking at understanding the basic principles of Laplace transform. The dVc dt becomes s times Vc of s minus the initial condition. Okay. But we also have to remember in this particular case that the principle of the transfer function is that it is a relationship between output to input. And so this piece of information about initial conditions is spurious information. Okay? It's extraneous information. It's extra information that I don't need. If I had asked for the problem, I said solve for this in time, then yes, the initial conditions make a difference. But I'm only looking for a relationship between input and output. And so what we need to do here is we need to remember that the principle of the transfer function is that we ignore initial conditions in transfer function derivation. Okay, when we derive a transfer function, it's been ignored. If somebody gives us a model of a system as a transfer function, they're only giving us the information about input to output. If they want us to solve then the dynamics of the system, then we have to get it back to its differential equation form, retransform the problem, and then put in the initial conditions. But that's not what we're solving for here. We're looking for transfer functions. Okay? And so we would need to say that in this case we ignore this point here. And then finally we need to understand that 1 over L integral of Vc dt, this integral transforms to Vc divided by s with a scaling of 1 over L. Okay. So now all these terms, one by one, can become transformed. And then what we have to do next is then transform algebra. Okay. Any questions about problem number 1? You'll notice that when we wrote the nodal equation here, this resistor doesn't enter into the problem anymore, because no matter what the resistance is here, the current flowing through here is going to be I1. Okay? So it makes it easy for me to grade. If I see R's in the answer, I said they've messed up basic circuit analysis. Okay? Any questions? Okay, so those are the basic principles. Understanding what is the definition of a transfer function, that it is a ratio in the transform domain, understanding how we can use superposition to simplify problems, understanding how to properly transform variables. Okay? You could probably save a little bit of time and not even do this. You could redraw the circuit here and put in all the transform impedances, you know, these terms like this. Okay. So we have to understand basically the basic science of circuit analysis. Okay, this is just circuits. And then finally do the transform algebra. Okay. All right. You'll notice that because there's 12 problems, not any one problem is really worth a whole lot. So that's one of the problems with the final exam is you're doing a lot of work for a few points. All right, the next problem takes this a little bit further. In case we fail to understand how to do circuits, we can recover some points, at least trying to understand, again, some of these basic science points, superposition, the transform concept, and then transform algebra. But we do it now with a time domain equation. Okay? And so what we have to do is we're trying to find here the relationship between input to output, and we're told that the impulse function, the input was a impulse function. Okay, and so that means its transform variable is just equal to 1. Okay, that makes life easy. The output response is this, so we have to transform this to y of s. Okay, and again, we do it term by term, applying superposition, and we have to do a transform of e to the minus 2t. And I give a transform table. E to the minus 2t is going to be 1 over s plus 2. And then we're going to subtract off 1 over s plus 3. And so this is understanding how to basically transform a time domain expression into Laplace transform, or the transform domain. So we use this particular transform pair and this particular transform pair. Okay, there's no differential equation involved here, so some of this is extraneous information. And so the transform, the Laplace transform here is just going to be this answer here. Okay, the transfer function we're looking for is the ratio of output over input, but the input is just 1. So you could leave it there. We could do a little bit of transform algebra if we wanted to. Okay. But if you left it here, it would be okay. Any questions about this particular problem? Okay, this is the answer.
How long is the test compared to the usual test?
Final exam period is 2.5 hours.
How long would it take us compared to the
It's 12 problems. Okay. Okay. So the question is, how much algebra do I need to carry out? You need to do as much algebra as you need to solve the problem. If it was me, I would leave it here and go on to the next problem. If I ended at the end of the exam and I have some extra time, you might go back and work on it, but it's really not critical because you don't need to do anything more with this transfer function in this problem. If you needed to find something else in the problem, like maybe sketch a root locus, yeah, then you would have to do more algebra, but that's not the case here. Okay? Okay, so this is problem number 1. Let's take a look at problem number 2. So now we're looking at the concept of a transfer function for a feedback system. And so this has been the focus of the entire semester. One of the things that we want to walk away with is understanding that feedback changes the behavior. And so now we're given a model where we have different blocks, and we know each of the model to the different blocks, but we want to determine what is the relationship between a particular input and a particular output. And again, once again, we see that we have a system where we have multiple inputs. This is an input, N is an input, R is an input, Y is an output, E is an output. But we're looking for, in particular, the relationship between this input and this output. Okay. And so we need to understand that the relationship between signals and blocks is algebra. And so you can, one of the underlying concepts is block diagram algebra. Okay. So for example, one of the block diagram algebra things that we could say is that this signal, let me call this y. Y of s is equal, this signal here is the output of C, but C has an input, and its input is the output of B, and B's input is E. So one of the things that we know is the relationship between E and Y is that we have B times C of S operating on E of S. So this is just algebra, just multiplying it together. Okay. But carrying this a little bit further, for a single loop, there is a concept for a single loop. One of the concepts is that we use this algebra, we derive a relationship between output over input is going to be forward gain divided by 1 minus the loop gain. And so we want to understand what is the definition of forward gain, what is the definition of loop gain. But this equation only applies for a single loop system. If you have a multiple loop system, this equation cannot be applied directly. And that's what this next problem is. It's a multi-loop question. And so if you apply this equation to this problem, we will get tripped up. Okay? So in this particular case, the forward gain between input and output would be these three blocks and pick up all the signs appropriately. So in this case here, the forward gain is minus ABC in the S domain. Minus ABC. 1 minus, and then now the loop gain is everything in the loop. Okay? And we have to distinguish the difference between gains, models, and signals. And so the proper answer for this thing would be minus B times C of S. Okay, so this is the loop gain. A and D are not in the loop. E is not a gain, it's a signal. Okay, so it's outside the loop. And notice how we take care of this sign here. And then we have to do a little bit of block diagram algebra. Any questions about the first part of problem number 2? The second part is recognizing that this equation that is just written up here only applies to a single loop. But this is a system now with multiple loops. And so we have to do a little bit of work. We need to first reduce okay, let's reduce this loop. And so this loop becomes equivalent to something that looks like this. Okay, starting from here, that's this arrow, and then this is this arrow, so it needs to go up like this. Okay, let's give it a name. A, B, C, D. Let's call it E. Let's call it H. Okay, we need to reduce this loop and call it H. And so H is going to be the forward gain from here to here, so that will be D of S over 1 minus the loop gain. The loop gain, again, is minus D of S. Okay, so call that H. And then now we've reduced this to a single loop problem. We're looking for a transfer function out between the input N, which is this point, and the output E, which is this point. So we need to know what to do with R and Y. We just need to ignore them. Okay. So in this particular case, now we're looking for a transfer function between E as the output and N as the input. And so the forward gain from N to E there's a minus sign here, there's a minus sign here, they cancel out. So we have a minus sign and a minus sign, they cancel out. And then we have this block that's been reduced, we'll call it H. Okay. And then we have the loop gain, 1 minus the loop gain in this case is B and C. There's a plus sign here and a minus sign here. This minus sign is inside the reduction. So we should have minus BCH. of S. Okay. And again, this is one of those situations where, in the interest of time, because you have 12 problems you're working on, I would be hard pressed to take off any points for this, because this is a pretty complete answer. It's clearly you understand that you have to reduce this loop. Enough has been written on the page that I understand that you understand that you have to reduce this loop. It's clear what you're reducing it to. You gave a clear answer for what that is, and you gave a clear answer for what the relationship is between this input and this output, and the rest of it is algebra. Okay? And my recommendation is go on to the next problem, come back to this if you want to clean it up later. But there is nothing erroneous about this problem. I've not asked for a reduced answer. Okay? Okay? So when the clock is winding down and you've got 4 points on your opponent, don't throw the ball. Okay? Take a knee. Problem number 3, ask the questions about stability. I need to understand, how do I determine stability? And in particular, the stability that we use in basic system analysis is what is known as bounded input, bounded output stability. Is the system bounded input, bounded output stable? It's abbreviated BIBO. Is the system bounded input, bounded output? And that means basically we need to understand that when we're dealing with transfer function, there can be no poles in the right half plane. No poles in the right half of the S plane. And that means no poles on the imaginary axis. Okay? Some people talk about that as being marginally stable. That's correct. But we're talking about bounded input, bounded output stable. Okay? I've used the joke before, is, nobody wants to date a marginally stable guy. So marginally stable is just as bad as being unstable. Okay, so I'm looking for here an understanding that these factors here in the numerator have no bearing on the stability. Do they affect the response? Yes, they do affect the response, but they will not cause the response to blow up to infinity. Okay, so this has no bearing. No bearing on the problem. No bearing on the problem because they aren't poles. So you need to understand the relationship between poles and zeros. And in this particular case, this was my attempt at a gift. We look at this and we recognize that we have poles at S equal to -1. That's this term. But we also have complex conjugate pair of poles at 1 plus or minus J2. Okay. So that comes from this factor here. Okay. And so this is not good. This term right here. That tells us that the poles are in the right half plane. And so to explain for full credit, we have a pair of poles in right half plane. And so the conclusion is that it is unstable. Okay. Okay, any questions? Concerns? All right. You might expand this or reduce it into a polynomial, plug it into your calculator. If this is kind of an old man's algebra, But if you recognize it, it can save you a few steps, a few seconds. Okay, now we're dealing with a problem where we don't have numbers, but we have variables, and so how do we address this? And so in this particular case, one of the concepts that we looked at was the idea of using something that allows us to work with variables, and one of the tools is the Routh-Hurwitz criterion. So there's two principles here. We're looking at, is this system stable? But we're only given a model of this part. And so one of the things we have to do is we have to find the ratio. We need to find the control system model. Okay, we need to find the control system model. And the control system model is something that we looked at earlier in the previous problem. So these same principles come out, but unlike the previous problem where you could have left the algebra unfinished, here the problem is going to have to be carried out. We have to carry through the algebra. And so we need to find the relationship y of s over r of s. In this case, it's going to be forward gain over 1 minus the loop gain. And so we're going to have g of s is the forward gain from r to y. The loop gain is 1 minus, the loop gain here is minus g. So we have g over 1 plus g. And we're going to have to do this substitution because we're looking for the stability of the control system. So we have to do some algebra. Now here, careful algebra is important. So I'll carry out a step here. So we have k over s squared plus a1s plus a0 over 1 plus the same thing. Multiply top and bottom by this thing, and we get k over, and in the bottom now we'll have s cubed plus a1s squared plus a0s plus k. Okay, so careful algebra is important here. S cubed plus a1s squared plus a0s plus k. Okay, that's just reducing this. And now we have to understand that we have to study this. And so the next principle that needs to apply is the Routh-Hurwitz criterion. So I'm looking to see if we understand how to set up the Routh-Hurwitz array. And so we would set up an array s cubed, s squared, s1, s0. Populate the first two rows by putting in a 1, a 0, and then k. This k goes here. Okay. Now I'm calculating all these things. And knowing how to apply the Routh-Hurwitz criterion, we have to analyze it and determine what is going on basically in this first column. Routh-Hurwitz criterion would have to be reviewed. So we had to know how to calculate these coefficients. This is algebra. Here, algebra is important. Can we find those coefficients? And we do know what to do with this first column of coefficients. Okay. In this particular case, this coefficient started off as a positive number. So one of the things that we know is that they're better. The rest of these all have to be positive. There can be no sign changes. So A1 has to be greater than 0. And then these coefficients here are going to reveal some other algebra constraints on A0 and so forth. Okay. Okay, so understanding that we have to reduce the model to seek the model that we are looking for, and that we're looking for stability of the control system, not the stability of G. Okay, so sometimes we'll see people, they'll say, oh, G's unstable. There's a pole on the imaginary axis. That's true. But what about the control system? Okay, so this is important. Do your algebra carefully and then apply the Routh-Hurwitz criterion. Okay, problem number 4 is about step response characteristics. Okay, and so we're given two characteristics. This is a two-part problem. One characteristic that looks like this, starting at time t equal to 0. So the plots are with respect to time. These are step responses in time, step response characteristics. These are in time. And we want to know that there is a relationship between simple step response characteristics and simple models. And this looks like a first order model. And so we're looking for a model of the form k over tau s plus 1. And there are two parameters that we need to find. Okay? And we need to understand that k is what we call the DC gain. And it's going to be the ratio of output to input. And so we take a look at the output here and start off initially at 0. So we have, and then it went to minus 1. And so this change in output, this is the output change. The change is minus 1. And so the DC gain here is minus 1 divided by the input. The input step function having a magnitude 2 is applied to a linear system. And so this is the number 2 here. So the magnitude 2 comes down here. And so this is the DC gain. That's that parameter. And then we look at the settling time here. And we know that that settling time within 2%, we need to eyeball here and say, where's 2%? You know, maybe right about there, 2% settling time. This number here is approximately 4 times tau. Okay, so we can find tau. Tau is equal to 0.6 divided by 4. Okay. So if I saw something like this, this suggests to me that you understand that this looks like a first order response. That's very clear. And you gave a clear answer for what k and tau needs to be. Okay. This is a second order response down here. And so we're looking for a model of the form k omega n squared s squared plus 2 zeta omega n s plus omega n squared. Okay. And so the other way to look at it is that this system has poles at s equal to minus the real part plus or minus j imaginary part. And you can give answers for the real part and an imaginary part. One of the things that we can determine, for example, is we can take a look at the settling time. Now let's call this the settling time. Settling time is equal to 3. And that settling time is again equal to 4 times the time constant. So tau is equal to 3 over 4. But the time constant is 1 over the real part. And so that means the real part must be equal to 4 over 3. So now this is known. Okay. And then the overshoot, we can take a look at the overshoot. Okay. The overshoot percentage is going to be, I got an overshoot, looks like about an overshoot of 1. The overall magnitude of change is 4. So the overshoot percentage here is 1 over 4. That's 25%, or 0.25. And there's a formula for that. It says that 0.25 is equal to e to the minus real part over the imaginary part times pi. And so we need to have this somewhere on our page. And we know the real part, so we need to be able to find the imaginary part. Solve for imaginary part. We still have to find k. We're told that this is a second order transfer function, and it yields a unit step response. That means the input was 1. The input was 1. Input is equal to 1. And the output change was equal to 4. Output change was equal to 4. And so we could right away now say that k is equal to output change over input change, and that's equal to 4.
Okay.
All right, so those are the first 4 problems. Come back on Wednesday. We'll continue marching forward and try to cover a few more of these problems. I'm going to give you back exam 4 right now.